Greetings and welcome to week 4, unit 3 on categories of engineering knowledge. In the earlier unit, we understood what engineering is. Of course, you can have your own opinion, but as we kept on saying, first thing that you have to do is engineering is not a subset of science. And it is not characterized as applied science. If you accept, then you can have on the details your own opinion. Okay. In this unit, we will try to understand the categories of engineering knowledge, especially as given by Professor Vincenti. Now, coming back to the same issue, engineering and science, what is the relationship between the two? In the earlier unit, we said one standard prevalent opinion is engineering is applied science. That means it is not a subset of science. But if one accepts the engineering somewhere between, let us say, what Professor Vincenti stated or Henry Petrosky stated, then the relationship between science and engineering is like this. There is intersection between science and engineering, plenty of it, which we will call it applied science, that can be as large as you want, as you feel. But there is something still outside science that is called engineering. And then if I ignore all this part, then I am ignoring some important aspects of engineering. So I am not ignoring this applied science part. So that is still part of engineering. But still, more than applied science, there is something else in the engineering. So if you take this view, then we go with Vincenti. He attempted to identify the nature of engineering knowledge. I refer to the same book as in the previous one, What Engineers Know, How They Know It. And there are several others who attempted to characterize engineering knowledge. If you put all of them together, they lead to similar categories of knowledge. They may use different labels though. So categories of knowledge as per Vincenti, 6 he identified: fundamental design concepts, criteria and specifications, theoretical tools, quantitative data, practical constraints, design instrumentalities. These are the 6 categories of knowledge as per Vincenti. Whether these are additional to the general categories or not, we will presently see. Fundamental design concepts, what are they? These refer to the basic principles, ideas or mental constructs that define the nature and purpose of an artifact and guide its design, even if they are not always formalized or quantified. Sounds a bit complex. They often shape the designer's initial approach to solving problem. Fundamental design concepts are what we call as emergent properties. This particular view that it is an emergent property, what does it mean? An emergent property is a characteristic that arises when simpler components interact at a system level, something not evident when you look at the parts individually. This is true at social level or even a artificially designed system level. When you put so many parts together, so many subsystems together to work, something emerges out of that. So what emerges out of that property cannot be predicted merely from the understanding the individual subsystems or parts. It is put together. Like the extreme example is, you have 100 billion neurons and they have a few tens of trillions of synaptic connections. When you put such a complex thing, what emerges out of that? People consider the consciousness, so-called consciousness, is a product of interactions between so many elements interacting with one another. Now that is still debatable, but what I am saying is, at least consciousness, something happens in the brain, and brain has a few tens of trillions of synaptic connections. Okay, so certain properties emerge out of interactions between all the subsystems and elements of the system. So fundamental design concepts are emergent from historical practice, used from systemic integration, from interactions of constraints. It doesn't emerge from below. It is by practice, by years of practice, or by intuition. You say it is likely to happen if you do like this. You intuit on that and you try it out. And then possibly whatever that you have can be explained by the underlying the component's behavior. That is possible. That is emergent property. So fundamental design concept is an emergent property. Some examples of FDCs: rotational motion for efficient energy transfer. Somebody felt that rotational motion, you can effectively transfer energy from one position to the other, one form to another. So the IC engines and wind turbines, they all are the subsequent results of that. So the rotational motion for efficient energy transfer is a fundamental design concept. Now it may even sound like already a scientific principle, but when it emerged, it did not come from below. It emerged and then it was explained in terms of the underlying science. Heat dissipation through fins. Engine cooling systems and heat sinks are result of that. By somebody felt that by putting fins, I can increase heat dissipation. And subsequently can explain why exactly the heat dissipation can effectively take place. Digital representation of analog information. That is, I can convert analog information to digital form and do many more things with that. Reaction equilibrium control. Mass transfer in counter current flow. Load distribution through triangular forms. Somebody kept on experimenting and they felt by using triangular forms you can distribute the load, and it becomes part of the standard practice as well. Modularization in software engineering. Once it is implemented, it looks quite natural, but when first it emerged, for example, even the von Neumann's idea of computing, that using memory as a part of the device, that you can make it perform many things in an electronic circuit, and that became the computer kind of thing. So it is good to acknowledge whenever you are solving a problem, what are the fundamental design concepts that you are utilizing. So you can right away start with that. And then for me the most important is criteria and specifications. Criteria are the goals are desired characteristics of an artifact, what it should do or be. And specifications are the quantitative or qualitative measures that translate criteria into testable or designable terms. Together, they define what constitutes success in a design before actual modeling, invention, or fabrication. Because all engineering activities start with the criteria and specifications. If you want to turn on a lathe, if you want to turn a rod on a lathe, what is the you have to define the goal, right? You want to turn it to a particular diameter with a certain accuracy. Now, unless you do that, just say turn some shaft that is given to you, somebody will have to ask question to what diameter and to what accuracy. You cannot be vague about it. You can say any diameter less than one inch. You cannot give like that. You have to give a specific dimension and also to what accuracy you need to build. You need to turn. So for every engineering activity that you ever likely to get involved, whether the once you come out of the college and then join any organization, whatever you do, there are always a set of criteria and specification. And unfortunately, in engineering programs, those two words practically do not appear in any part of that. If a graduating student is asked, what should be the accuracy of this, should be the accuracy, they'll say as accurate as possible. That's all. They won't give numbers. For example, even if you give the numbers, do you have a feel for those numbers? What do those numbers mean? And that part is never part of most of the courses that are offered. That has to be brought into the curriculum. All engineering activities start with criteria and specifications. Inappropriate criteria and specification can lead to rejection by the customer or cost overruns. Let's say you have a power supply, an electronic power supply. One characteristic, one criteria is regulation. What is the regulation level? If you say, I want to have a 5 volts power supply with a regulation of 5%, that is one specification. Somebody says, I want to have a power supply, 5 volts power supply with 0.01% regulation. Circuits may be similar, but a 0.01% regulation power supply will cost at least 100 times the cost of 5% regulated power supply. That feel an engineer must have. Otherwise, he is not, you are not doing engineering at all. Okay. So criteria and specifications are very important. They have to be somehow brought into as many courses as possible in an engineering program. Of course, these criteria are not always quantitative numbers. Sometimes there are qualitative measures as well. Samples of criteria and specifications. Vibration amplitude must be less than or equal to 0.1 mm at 3000 rpm. Structure must withstand 500 kilonewtons with a safety factor of 2.5. Power loss in transmission line should be less than 5% at maximum load. System must boot in under 5 seconds from power on. Yield must be greater than 90% for target compound at 300 degrees centigrade. There will be, especially in making integrated circuits, manufacturing, there is a huge difference between a yield of 95% and 96%. It can make a tremendous economic change for between that percentage change. Effluent BOD should be less than 30 mg per liter after treatment. System must have less than 1 undetected error per billion operations. These are criteria and specifications, and continuously the student should develop a feel for these numbers. Your specification should not be unreasonable. If it is unreasonable or it is way beyond the requirement of the as per the application, then you are unnecessarily making it very expensive solution. Then come the theoretical tools, something that you are all readily familiar with. Theoretical tools are abstract symbolic frameworks that assist in the conceptualization and analysis of engineering problems, especially from science and mathematics. No problem with this. These include mathematical theories, physical laws, engineering specific models like beam theory, control theory, computational theories, finite element methods, signal processing. Actually, they are the same as conceptual knowledge that we have already dealt with. Okay, they are no different. Samples of theoretical tools: Newton's laws of motion, finite element analysis, elastic beam theory, fluid mechanics equations, complexity theory, orbital mechanics. Quantitative data: measured or measurable numerical information that informs or supports engineering design decisions. Quantitative data includes empirical measurements, experimental results, performance metrics, statistical data, numerical results from field trials and lab tests. These are the quantitative data. Actually, these are the same as factual knowledge. Okay, you are talking in terms of number. Something should be this or something is that value. You conduct an experiment, you get some numbers, and that is a factual information. Okay, which is fairly so. Factual knowledge includes both descriptive as well as prescriptive data. Samples of quantitative data: stress strain data for steel, friction coefficients for bearing materials, concrete compressive strength, soil bearing capacity, resistivity of copper and aluminum, processor clock speed, lift and drag coefficients. Then you have practical constraints. These are non-theoretical real-world limitations. Limitations can be economic, environmental, manufacturability, legal, ethical, social, or organizational. These are generally not part of engineering science or science subjects. But neither they are the way our engineering subjects are offered, they are not part of that either. These shape engineering design decisions. Without this, and that's why they are now getting reflected in the program outcomes given by the NBA. These constraints may not emerge from scientific or technical theory, but directly impact feasibility, safety, cost effectiveness, and acceptability of a design. They are an array of less sharply defined considerations derived from experience in practice, considerations that frequently do not lend themselves to theorizing, tabulation, or programming into a computer. So there are several factors which we call them as practical constraints. You have to operate within that. Where do they come from? You cannot theorize easily on that. They are constraints given to you. somebody, the end user says it should be like this, you may not have a choice. If you want to meet the customer's requirements, you have to operate under that constraint. Samples of practical constraints. Maintenance accessibility. A product should be designed in such a way you should be able to, you should have access to all parts of that readily for maintenance. How do you theorize that? Local building codes, site soil conditions, backward compatibility. This is generally requirement for all very major software things. That is, if I upgrade my software, my previous program should also work with the new one. That is backward compatibility. Without that, the new product may not be acceptable. Then come one word which is not familiar in the context of engineering programs, design instrumentality. Design instrumentalities are the intellectual and physical tools, including procedures and systems, that help engineers generate, manipulate and communicate design solutions. Remember all the three: generate, manipulate and communicate design solutions. These include conceptual methods like design heuristics or failure analysis techniques, representation tools like CAD, diagrams or schematics, analytical tools like optimization algorithms, organizational procedures like design reviews and checklists. All these are called design instrumentalities. They are neither purely theoretical nor purely empirical. They are practical aids developed through engineering experience and refined through use. Like in all software development projects, you have what are called design reviews. Where did that procedure come from? People found from practice that it is good to do that, and then once you do that, how do you conduct your design review? You develop the procedure. Some samples of design instrumentalities include failure modes and effects analysis, FMEA, load path diagrams. That is, in that particular project, you use load path diagram. Somebody says, the project leader may say, or the members may suggest that we will use load path diagrams. That's it. Circuit simulation software, we will work with SPICE. Version control systems, Git, flight envelope diagrams, Aspen Plus or SYS simulators, finite element models of biological tissues. Now come to the categories of knowledge specific to engineering. Of these 6 knowledge categories, theoretical tools and quantitative data can be considered addressed by conceptual and factual knowledge categories of the general type. So, if you are talking of engineering, we already said we will stay with the 4 general categories of knowledge, in which you have conceptual and factual knowledge. And if I remove those 2 from the 6 categories that are produced, the 4 additional categories that are specific to engineering include fundamental design concepts, criteria and specifications, practical constraints, design instrumentalities. Okay. So, these are the 4 categories of engineering knowledge that we work with, and how do they reflect when we go to how to write course outcomes, what is the format in which course outcomes are written. There we will make use of, and that should also kind of result in the way we want to instruct our students, or even possibly how do we slightly adjust the goals of an individual course in such a way that what a teacher considers important aspects of engineering knowledge are addressed. In the next unit, we will try to present taxonomy tables to represent two-dimensional nature of revised Bloom's taxonomy and revised Bloom-Vincenti taxonomy. It's a kind of a simple graphic tool which can readily help you visualize things. Okay, and thank you for your attention.